got a few people in here. Hey everyone, glad you could make it all tonight. And welcome back to our study group for designing data intensive applications. So, hopefully, this time with this recording software, I'll be able to actually get a recording out for our friends in the EU and onward. And in case you missed it last week, there wasn't really anything to read at all because it was all introductory. Basically, we went over the purpose for learning this topic and for learning this book, and we basically just discussed our expectations. And there is a summary, some slides, and a recording. Once again, thank you, Tommy, for recording last week in our data intensive channel on the Discord. And so this week, we'll hopefully we've read or not. You don't have to read at all. There's no hard reading requirement. Chapter 1, which deals with reliable, scalable, and maintainable applications. So, just some definitions first. Uh, as for what a data intensive application really entails, they don't necessarily have to be compute intensive. That is to say, require they don't particularly require much CPU power, but they do have to deal with a lot of data processing and the complexity of the data and how often it changes. Um, And these applications are built using basically abstractions, building blocks of commonly needed functionality that the author Martin Kleppmann calls data systems. And they don't necessarily have to neatly fit any one category. And for example, Redis, which is a pretty popular tool for web applications these days, can serve as a database, a cache, or even a message queue, which to me is pretty cool. And often these systems are put together to create more complex data systems satisfying a range of requirements. And when we discuss these systems, a few good questions arise, and they tie into the three concerns that the chapter deals with. And one, how does the system tolerate unexpected behavior, and how do we ensure that it works as it should? How does a system tolerate increased load, and how do you maintain good performance when the load increases? And how do you design a system that is easily maintained and can be extended as requirements change? And those three concerns are related to reliability, scalability, and maintainability. So, sorry. As for reliability, it can basically be summed up as ensuring that a system works correctly even when things go wrong. And those things that do go wrong are faults, and faults can lead to failures where things actually go down. Can everyone see my screen right? It's good?
Mhm.
Okay, cool. Thank you. Just confirming. And what we're trying to do basically is create fault tolerant or resilient systems. And that can be achieved through a few things that Kleppmann categorizes into hardware, software, and basically human management. As for hardware, you can introduce like redundant components and provide software techniques for any one machine failure in a multi-machine system. In software, basically, you can provide monitoring, logging, and ensuring that you think through your assumptions about the design of your architecture. Um, More often than not, software faults correlate across systems, so a fault can spread among the system, and that can be a pretty big problem that's hard to debug. But the hardest thing really to manage and debug are humans, since we're notoriously unreliable. And a few things that we can do to help ensure fault tolerant systems is to give developers like proper sandbox environments where they can kind of feel free to experiment and test as they please. ensure that they write unit tests for their code, um, and generally provide good management to them, which is beyond the scope of the book. And one big takeaway that I got from this is that reliability is often an obligation and not an option. You have user trust and money that's on the line. If your service goes down, then that can cost millions of dollars and a lot of bad reviews. Later on in our discussion, I'll talk about like one particular startup that I found on the net whose service reliability is often so bad that it's what I think the primary cause for customer complaints. And in this book, Kleppmann brings up in this section Netflix's Chaos Monkey, which is basically a uh, service for testing reliability, which actually isn't the only thing Netflix has in its arsenal or had in its arsenal as it's not maintained anymore. They actually have a range of services codenamed the Simian Army that tests reliability, including one fun one called Chaos Gorilla, which simulates an outage of an entire Amazon availability zone, which I presume is pretty catastrophic for any software team. And there's also a startup in this space called Gremlin, which provides failure as a service. Um, and these two things can be combined under the field or term chaos engineering, which is where basically teams experiment on systems to enable and confirm fault tolerant systems. And now, as for scalability, so scalability can basically be described as the ability for a system to cope with increased load, which, as we'll see, is heavily dependent on the application's architecture. And more often than not, people will talk about a tool in terms of X or Y doesn't scale or cannot be scaled at all, which isn't exactly a productive conversation. And so Kleppmann recommends that discussions about scalability should center around how to deal with growth or how to add additional resources to deal with increased load. This comic to the side kind of is related to that statement. And as I said before, is dependent on architecture. And as for load, um, sorry, load is often described in terms of load parameters, which are numbers or stats that describe commonly used operations, and performance being, sorry, performance being things such as response time or throughput, which is heavily dependent on the application itself. And in web applications, commonly it's response time that's used as a performance metric. And under this section, Kleppmann used Twitter as an example, and how it basically Twitter scaled its um, posting and home timeline to fit increased user needs. Sorry, 1 minute. And last week, if you scroll up in the data intensive channel, Rodri, I can't see if Rodri's in the chat, but he shared a really interesting article on building scalable newsfeed applications, which actually mirrors the architecture that Twitter used and basically the architecture that was discussed in the textbook, which is pretty cool. And another neat video that I found on the net that I would recommend any person to watch is, I can't exactly see. the darn bars in the way. But how we scaled Dropbox, in which I believe a backend engineer or maybe like the co-founder um, basically has a talk on how Dropbox architecture has changed and the various load parameters and issues they've run into over time as their architecture has evolved. So when when we're gauging and coping with load, there are a few questions that we want to ask. What happens when load increases and resources are the same, and how performance is affected? And how much do we need to increase resources to keep performance unchanged? And there are two approaches to this. Well, yeah, two of a few. Scaling up versus scaling out, wherein you basically move to a more powerful machine versus distributing the load across multiple smaller machines. And scaling up often is referred to as vertical scaling, and scaling out is also referred to as horizontal scaling. But good architectures often use a mix of both. And not included in this slideshow, but Kleppmann also mentions is a term elasticity, in which systems can automatically provision more computing resources when um, increased load is detected. And I believe that's the foundation for a few of Amazon's web services. But some systems are scaled manually, and there's not exactly a one size fits all solution. And more often than not, it's like I said, it's dependent on the application. It's often easier to scale out some stateless services as opposed to something like a database. And there's some pretty cool wisdom that Kleppmann provides as to how to deal with stuff like that. Oh, and one more note that I forgot to include was that a lot of the time you'll just have to consider like what your load parameters are and what assumptions about common operations that will be made, and that can really affect how you gauge performance and what changes need to be made. And as for the last point in the chapter is maintainability. And Kleppmann discusses legacy systems, which I'm sure our mentors have run into multiple times to their frustration. And they require maintenance and adaptation to new platforms or reduction of technical debt. And it's for many, it's not really a fun job. And a key point that's made here is that systems should be designed as to provide easy maintainability and extensibility. So they should be easy to evolve and easy to upkeep. And three principles that are discussed are operability, simplicity, and evolvability, all which are very important. So operability is basically ensuring that your application is easy to maintain and keep working correctly. So that kind of ties in back to the principle of reliability. Simplicity, which is creating good abstractions and removing accidental complexity, which often arises in the implementation of a solution to a problem. And evolvability, which is just I believe, the agility of which a system can adapt and be modified to fit new requirements. And often these requirements will change over time. And so evolvability is also closely related to simplicity, just because the more good abstractions that you have in your system, the easier it is to enable evolvability in the end. So that's the end of my slides. And I guess